This is the first in a series of videos about catalysis. We'll talk about catalysis, which is the process, and catalysts, which are the things that do the process, how that's related to kinetics. We'll draw reaction diagrams and look at how a catalyst affects the diagram, and we'll talk about how to connect kinetics back to equilibrium. So we hinted at the last video. We looked at I- in this mechanism, and we said it was used up in the first step and regenerated in a later step and didn't appear in an overall reaction. So this is called a catalyst. Catalysts are things that we introduce into the reaction at the beginning that are used up and reproduced at the end that help the reaction to go faster. So a catalyst increases the reaction rate without being used up. The W/O is without being used up. And remember, when we talk about something affecting the reaction rate, we are in the realm of kinetics, how fast something goes. What it doesn't do is it doesn't affect the world of equilibrium. Does not change the value of the equilibrium constant and it doesn't change the delta H. So there are three languages that we talk about in chemistry. There's the language of kinetics, there's the language of equilibrium, and delta H is from the language of thermodynamics. Those are the three ways of discussing how a reaction proceeds. So the catalyst only changes one of these. It only changes the kinetics of a reaction. So let's look at a reaction diagram and we'll illustrate how that works. So we're going to make a nice big diagram, take up half the page with it. Reaction progress versus energy. And we're going to return to our simpler looking picture here, not the one with the many bumps that we had in the video with the intermediate. All right, so here's our product energy, here's our reactant energy, and then kinetics is all about the journey in between them. So we may have an activation energy hump that looks something like this. So we can draw in some of our basic features. So we can label the thermodynamics delta H, which is the difference between product and reactant energy. We can add that to the diagram. And remember, we said we can also draw in the delta H for the reverse. So if we're going from reactants to products this way, final minus initial is going to be a negative delta H for the forward. If we were going in the reverse reaction, the reverse direction from the right side to the left side, products minus reactants would be a positive number, like this. This would be our delta H of the reverse reaction. And both of these numbers are, oops, we used blue, didn't we? They're thermodynamics numbers. Thermodynamics is path independent. It doesn't matter what happens in the middle. We only care about how do we get from product energy to reactant energy. And we can mark the activation energy, all the skills we've learned so far. Activation energy is, actually we're gonna put it over here. The difference in energy between the reactants and the highest energy point. So we can label activation energy for the forward reaction, and we can label it for the reverse reaction. So in the reverse reaction, this side would be the reactant side. So that's our activation energy for reverse. These are all things we've labeled before: delta H forward and reverse, and activation energy forward and reverse. And activation energy is a kinetics number. And we can also label intermediates, which we don't have in this problem. Okay, but in this page, in this video, we're talking about catalysts. And catalysts are going to increase the reaction rate, and they're going to do that by decreasing the activation energy. So the process, the path, is going to look a little bit different. There we go. So that's going to be my catalyzed reaction. So if I wanted to label the same thing, my delta H forward and my delta H reverse would be the same, right? Because the reactant energy hasn't changed and the product energy hasn't changed. The destination and the origin are the same for that catalyzed reaction. What has changed is the activation energy. So now my activation energy for the forward reaction is a lot smaller, right? It's about half the size of the uncatalyzed reaction. Oh, we should label this. This is going to be catalyzed in red, and this is our uncatalyzed in black. Okay, so our forward activation energy is smaller, and our reverse activation energy is also going to be smaller. From the reverse reactants up to the highest point on the graph. So this amount is smaller than the uncatalyzed, which was this amount. So the activation energy forward and reversed were improved. Let's write that over here. Kinetics of forward and reverse reactions are improved. So that'll come into play more later, but just remember that just because it's making the reaction faster doesn't mean it's only speeding up the forward reaction, it's also speeding up the reverse reaction. So the role of the catalyst energy-wise is to change the activation energy by changing the mechanism. So catalysts change the reaction mechanism, that series of elementary steps that tells us about the path between reactants and products in real life. When you change the mechanism, you change the activation energy. That's where the activation energy comes from. And that's why the shape looks different. There's a bump in a different place, or there might be a different number of bumps, and the activation energy, the highest point, is different. So those two things have changed without changing the overall reaction. So the reactants are the same and their energy, and the products and their energy are the same. So we have changed the mechanism and the activation energy, but we didn't change the overall reaction, right? Let's look at that one we had on the previous page. I minus was our catalyst, and even though we had a catalyst involved in this reaction, it wasn't present in the overall reaction. So we could have done the reaction without it, and it would have still went, the mechanism would have been different, but we would have still ended up with the same overall reaction. The role of the catalyst is to improve the kinetics by decreasing the activation energy and by changing the mechanism. So in the next video, we'll do an example of a situation where a catalyst was used to decrease the activation energy of a particular reaction.